All right, hello and welcome to round 2 of Mr. Quark's physics videos. Last week we talked about circular motion and using Newton's second laws to solve problems involving objects that are moving in horizontal circles. So things like, a car going around a bend or a turn, or what else is there? Or like if you whirl something over your head horizontally, like a slingshot, something along those lines. Now we're going to move on to vertical circles. So first we talked about Newton's second law, so F naught equals ma. And when it comes to circular motion, we're going to replace Newton. We're going to apply Newton's second laws in a little bit of a different way, where we use the centripetal version of that equation. Okay, so first we're going to start off by just going through some examples of drawing free body diagrams for certain situations, because as you guys know, the first step when you're solving any kind of force problem is to just start with a free body diagram. If you don't have an idea of what the forces are acting on an object, then there's no way you're going to be able to solve it out properly. All right, so let's say the first example, you have a skateboarder. Let me make it bigger. Oh, that's too big. That's perfect. You have a skateboarder, and he or she is going on a half pipe, and at this particular moment, they are at the bottom of the circular half pipe. So let's draw a free body diagram. And well, there's the normal force of the bottom of the ground pushing upwards on him, and there is the force of gravity, Fg, or the weight force. Now you might think again that there's a force pushing him sideways, but if he's not actively pushing, using his legs to propel himself forward, there's no force causing him to go forwards. It's just inertia that's causing him to go forwards at a certain speed. He's not accelerating at that moment in the x direction. Now, second example, you have a kid is playing with a yo-yo, and he's swinging the yo-yo. Actually, let's just move to let's switch up the order of the examples. Let's say you have the same skateboarder, except he or she has just dropped in. So they just drop in. What is the free body diagram? What does the free body diagram look like? Well, in this case, now the ground is pushing sideways on him, right? And the force of gravity is pulling him downwards. Okay. Now, the third example, let's say again, now it's the yo-yo kid, and he's swinging the yo-yo around his head and a kind of around the world, basically swinging it by his side. So the yo-yo is attached to a string, and it's moving in a circle. Okay, maybe like this. So what is the free body diagram acting on that yo-yo? Well, there's the tension force of the string pulling it downwards, and there's the force of gravity acting on the yo-yo itself. And again, there's no force sideways, because at that moment, he's moving in uniform circular motion, so the yo-yo is moving at constant speed. There's nothing accelerating him sideways. The only acceleration is responsible for turning him, not for changing its speed. So it's going to be moving at constant speed. And the last example is a similar case, except now the yo-yo is at the bottom of its path. And like that. And so the yo-yo is now at the bottom of its path. So what does the free body diagram look like? Well, the tension force is not pointed upwards because the string is pointed upwards. And there is the force of gravity pulling it downwards. Okay. Now, some notes. So this is the first step you should do for any force problem, right? We've correctly identified all of the forces. Great. Now the second step is to define what your axes are, right? So we have to know, especially for the centripetal, when we're talking about centripetal forces, we have to know which axis is we're going to be using this one for. Which axis is the centripetal axis, or the axis that is causing the thing to move in a circle. In this case, since we're talking about vertical circles, the centripetal axis is the y-axis, because it's the reason why it's turning in a circle. Actually, that's not necessarily true. The centripetal axis is the direction of the force that is causing it to go in the circle. So let's look at example 1. The only forces acting on that skateboarder is just the normal force and the force of gravity, and they're both acting in the y direction. Now you have to ask yourself, is this guy at that moment accelerating centripetally, or is the y-axis responsible for making him move in a circle? And the answer is yes. So once we determine that, we can write out our equations. So just a quick note before you write out your equations. What direction is positive and negative in a circle? Well, in the last video, I said if you have a circle, anything pointing inwards to the circle is positive, and anything pointing outwards of the circle is negative. So we're just going to follow that. There is another way to do it using our normal positive and negative axes, but we're just going to stick with this one because it's simpler for now. So for this one, we start with the net force, F net, is equal to ma. And we know, we just clarified that the centripetal force is in the y direction. So if we're looking at the y direction, we can replace F net with Fc, and we can replace A with AC, which is v squared over r. And just like we do in any other force problem, we can replace the centripetal force with all of the forces acting in that direction. So here we have the normal force is pointing towards the center of the circle, so it's positive. The force of gravity is pointing out of the circle, so it's negative. So we add those together, so we get normal minus the force of gravity. That's equal to mv squared over the radius. Okay, so this would be the equation that you would get for number 1. For number 2, let me just draw a line here. For number 2, our equation is going to look a little bit differently. So the only force that's causing him to go in the circle or turn is the normal force. The force of gravity is actually pointing downwards. Is that the centripetal direction, the downwards direction? Well, no, the direction he's turning in is towards the center of the circle, right? That's the centripetal direction. So we can actually make 2 equations here. One is in the centripetal direction. So that becomes Fc is equal to mv squared over r. And so the centripetal force is the normal force, because that's the force that is pointing towards the center of the circle, mv squared over r. The other equation that we would get is if we look in the y direction with the force of gravity, and so we would get Fg is equal to ma. And Fg is not responsible for him turning in a circle. It's just responsible for actually just speeding him up in that direction. So this is all we get here. Okay. I am going to readjust this real quick. Move this over. Okay, nice. God, I love this software. Nice. Okay. Now the third situation, you have the yo-yo, and it's at the top of its motion. So you have let's start again. F net is equal to ma. Well, both of these forces are pointing towards the center of the circle. So both of these forces are going to be responsible for its centripetal acceleration, v squared over r. Okay. And this would be the proper equation here. You notice I skipped a step. I didn't write out Fc is equal to mv squared over r. because you don't really need to. And then the last one is last one is actually that's not quite right. This is not quite right. Both of these. So remember, I said positive is into the center of the circle and negative is outside the circle. So actually, both of these forces point towards the center of the circle. So it should be tension plus the force of gravity is equal to mv squared over r. That's the correct one. I'm sorry about that. Number 4. Now we get the situation where the yo-yo is at the bottom of its motion. So F net is equal to ma. Both of these forces are in the y direction, so they're both related to its circular path. They both have something to do with why it is. They're both forces that are pointing radially away from the center of the circle, or towards or away from the center of the circle. So they're going to be centripetal forces and centripetal accelerations. If we add them together, well, the tension is pointing towards the center of the circle, so that's positive. The force of gravity is pointing away from the center of the circle, so that is negative. And so we add them together, so that becomes tension minus the force of gravity is equal to mv squared over r. And this would be our expression for number 4. Now, any question that I ask would be some kind of variation of these. Basically, you're going to have to write out Newton's second law for a situation like this, and you're going to have to solve for something. Now, obviously, I will give you the variables. So for the example number 4, I might ask you for what the tension force in the string is, and I'll give you the mass of the object, so you should be able to find the force of gravity. Well, you have the mass here. I might give you the velocity of the instantaneous velocity of the yo-yo at that point at the bottom of its motion, and its radius. So these will all be given. And then you should be able to solve for the tension. Now, in order to get the proper tension, you have to set up the equation in the right way. Okay? So, one last note. I'm going to do a quick example. And we'll call it a day. So, let's say you have a roller coaster and a loop-de-loop of a ride also roughly exhibit circular motion. If the loop has a radius of 7 meters and the mass of the person in the cart is 70 kilograms, and it travels the entire loop in 4 seconds, what is the force exerted by the loop-de-loop at the top and the bottom? Okay, so you have this loop-de-loop, and I'm asking for what's the force exerted on the roller coaster at the top and the bottom. So, I'm going to do the top. And so at the top, there's a normal force from the track pushing down along with the force of gravity. So the equation is going to be F net is equal to ma. And so since the center of the circle, they're both force pointing toward the center of the circle, it's the normal force plus the force of gravity is equal to mv squared over the radius. So we are trying to find the force exerted by the loop-de-loop, which means we're trying to find this guy, the normal force. The given variables are that the radius is 7 meters, the mass of the person in the cart is 70 kilograms, and it travels the loop in 4 seconds. So the period is 4 seconds, meaning we can use this. Using that equation for the velocity, 2 pi r over the period, to find its velocity. Okay, so if we're trying to find the normal force, well, we know the force of gravity is acting on the person in the roller coaster is just mg. So the force of gravity is mg, equal to mv squared over r. Mass is 70, g is 10, mass is 70. The velocity is it's 2 pi r over t, so 2 pi times 7 over 4 squared over the radius, which is 7 meters. And you would solve that, so that would end up being negative 700 plus, I'm going to simplify here, 70 divided by 7 is 10. 10 times 2 pi times 7 over 4 squared. You can plug that into your calculator, and you would get that, I guess I'll have to do that too, that the normal force is equal to plus 10 times 2 times 3.14 times 7 divided by 4 times 2 times 3.14 times 7 divided by 4. The normal force is equal to 507.8 newtons. Cool. Now, how about at the bottom of the loop-de-loop? Well, at the bottom, you've got the person sitting here feels a normal force from the bottom of the track, or the seat that he or she is on. And the force of gravity is actually acting downwards, just like always. So if you write out that's the proper free body diagram. If you write out the proper net force equation, we end up with F net is equal to ma. And since towards the center of the circle is positive and outwards is negative, the normal force is positive, but the force of gravity is negative. So we get this. And, well, we can do the same thing. The normal force minus mg. The only difference is the sign of the weight force. Everything else is the same. So we plug in our numbers, we get the normal force minus 70 times 10 equals 70 times 2 pi times 7 over 4 squared over the radius of 7. And we can solve that out. That becomes, well, now we add 70 times 10 to both sides, so it's 700 plus, again, I'm going to do 70 divided by 7 is 10, times 2 pi times 7 over 4 squared. And if we do that out, what we end up with is the normal force is 1,908 newtons. Now, just a quick real life example of what's going on. Well, when you're on a roller coaster, what happens at the top of the loop-de-loop? Well, you feel weightless. At the top, you feel weightless. And compared to the rider's weight, right? The rider has a mass of 70 kilograms. So his weight force, or his force of gravity, should feel like 700 newtons. So normally he feels 700 newtons of force pushing up on him from the ground, right? The reason why he feels that force isn't because his weight force is 700 newtons. It's because the ground is pushing up on him with 700 newtons of force to balance that out. Well, now, instead of feeling 700 newtons, he feels 507 or 508 newtons. So that's why at the top of the loop-de-loop, you feel lighter than normal. Sometimes you even feel weightless. Now, at the bottom, what do you notice about his normal force compared to his regular normal force, or his regular apparent weight? Well, at the bottom of a roller coaster, or at the bottom of a hill, you feel heavier. You feel way heavier, and that makes sense, right? The result we got was almost 2,000 newtons. Normally, he feels a weight or normal force, or his weight is 700 newtons, right? So the ground is pushing up on him with 700 newtons of force. Well, now the ground, the supposed ground, or the track is pushing up on him with almost 2,000 newtons of force. That's almost 3 times his weight, or his or her weight. So this is why when you're going on different rides, they manipulate how you feel your weight by using circular motion principles. Okay, so if in a question I ask you, oh, how fast do you need to be moving so that the rider or the object feels weightless, completely weightless? Well, if they really feel weightless, then they should feel no normal force or no contact forces. So really, you do the same steps, except there would be no normal force. So at the top of the roller coaster, for example, in part 1, the only force that would be acting on him, well, there's a normal force. But if he was weightless at the top, that normal force would be equal to 0. And then you'd solve it the same way, except, well, the normal force is 0, so all you have is the force of gravity, and you can find the speed that way. Okay? All right, and that's it for today. Good luck on the homework assignments over the weekend, and I'll see you guys in class. All right.